This video is not intended to mimic the construction or model the actual collapse of the 3 World Trade Center structures on September 11th. Galileo, the persecuted truther of his time, understood the problem of material strength and scale, and described it in his discourse on 2 New Sciences. Rather, my videos are intended to demonstrate fundamental laws which do not vary with scale. The laws of gravity and motion of falling objects are the same with a bullet, a bowling ball, or a building. The 3 largest structural failures in history all happened on 9/11. The National Institute of Standards and Technology, or NIST, was tasked with providing a report as to the cause of their destruction, and they concluded that the primary cause was from normal office fires. In their final tower report, NIST wrote, "The downward movement of the structural block was more than the damaged structure could resist, and the global collapse began." But in 2010, David Chandler wrote a paper called Destruction of the World Trade Center North Tower and Fundamental Physics. Citing Newton's laws, he concluded, as long as the roofline was accelerating downward, the upper block exerted a force less than its own static weight on the lower section of the building. So was there more force or less force imposed on the lower structure by the falling upper portion of the buildings? And who is right, Newton or NIST? We need to conduct some experiments, the arbitrator of competing hypotheses. Let's look at the motion of 2 falling bodies, a splitting wedge and a splitting maul. The motion of this falling wedge and the motion of this maul look similar as both fall through the log. But the wedge speeds up and the maul slows down when it hits the log. Let's review some basics. Velocity is a change in position over time. Acceleration, a change in velocity over time, and it includes both speeding up and slowing down. But for the purpose of this video, I will refer to acceleration as an increase in velocity and deceleration as a decrease in velocity, and uniform acceleration as a uniform increase in the rate of velocity over time. The word weight denotes a quantity of the same nature as a force, and the weight of a body is the product of its mass and the acceleration due to gravity, W equals mg. The apparent weight of a body in a particular reference frame is the force that gives the body an acceleration equal to the local acceleration of free fall in that reference frame. In other words, if you stand on a scale in an accelerating elevator, your weight will vary. Newton's first law predicts the behavior of objects when all forces are balanced. Objects at rest will remain at rest, and objects in motion will remain in motion. His second law is applicable to bodies where all forces are not balanced. The sum of all forces acting on a body is equivalent to the mass of the body times its acceleration, F equals ma. And Newton's third law applies to all bodies regardless if the forces are balanced or not. For every action or force, there is an equal and opposite reaction or force. David Chandler carefully measured the acceleration of the roof of Tower 1. Not only did it not experience any jolts as it fell, but it uniformly accelerated. And he also measured the fall of WTC-7 and found that it uniformly accelerated, falling at a total free fall for about 100 feet of its fall. The motion of both those falls was like the motion of my falling wedge because both uniformly accelerated with no deceleration or jolts. The French sometimes use a demolition technique called vernage. Careful measurements of the roofline of its fall indicates that it does not uniformly accelerate. Rather, it decelerates slightly when it hits each floor in accordance with the conservation of momentum laws. This momentary deceleration is similar to my maul as it hits the log. Using some old pipe and plywood, I built an adjustable ramp and placed it on a spring scale. If you put a bowling ball on it and roll it in the horizontal or x-axis, would there be any change in total weight? No. The sum of all forces in the y direction is equal. I tied a line to a bent cotter pin and pushed it into the thumb hole in order to hold the ball on a slope. Now, let's put the ramp at an angle. Is the total weight or upward force the same? Yes, because the system is in equilibrium in accordance with Newton's first law. But if we melt the line, allowing the ball to accelerate, will the apparent weight be more, less, or equal? The apparent weight is less, meaning that the upward force is less. When we increase the angle, the same thing happens. The apparent weight of the ball is less as it accelerates, and the steeper the angle, the more the acceleration rate. the less the apparent weight, and the less the upward force. That upward force is inversely proportional to the acceleration, precisely in accordance with Newton's second law of motion. An easier way to think about this is to suspend a spring scale by a rope from a pulley. If you drop the load, allowing it to accelerate, the apparent weight, and therefore the upward force, will vary in accordance with Newton's second law. I removed the Acme threaded rod from a jack, allowing it to freely move up and down, and bolted it to a spring scale. I replaced the Acme screw with a nylon line, and when cut with a torch, it will lose its structural capacity. Dropping the wood block resulted in an impulse or jolt momentarily reflected in the scale as increasing weight followed by a decreasing weight as the jack collapsed. But if we attach the block on top and torch the line, the block uniformly accelerates. And when the block uniformly accelerates, the force is less on the spring scale until it hits the scale. Let's remove the nylon line and support the top block with some sticks. When we yank out the sticks, the motion of the top block also uniformly accelerates, and this motion is like this motion, and like this motion, which is like this motion. The problem with moving scales, or one with big impacts, is that it's difficult to read. But what if we suspend a scale from the barn rafters and steady it with a cross stick so it doesn't twist? I made a spreader bar with 2 pulleys and placed a heavy weight in the upper sack and a light weight in the lower one, holding a load with a fishing line until it's cut. Now, when we torch the fishing line, the heavy sack uniformly accelerates downward, while the small sack accelerates upward. We can directly measure the reduction in weight due to the uniform acceleration. Perhaps the simplest way to envision the principle of decreasing resistive forces with uniform acceleration is to hang a bowling ball from a fishing line that can just barely support its static weight. Drop the bowling ball to the ground, and the fishing line holds because the accelerating force is reduced. But if we decelerate the ball before it hits the ground, the force increases, and the line will break. So it wasn't the acceleration, but the deceleration that broke the line. If a falling structure uniformly accelerates, then the apparent weight of the falling structure is less than when it was at rest. If the apparent weight is less, then the downward force is less, in accordance with Newton's second law. And if the downward force is less, then the upward supporting force must also be less, in accordance with Newton's third law. And if the upward force is less, then some other force must have weakened the supports. And that weakening force could not come from the falling body, because it would slow down that falling body, not allowing it to uniformly accelerate. Since the towers in World Trade Center 7 uniformly accelerated, then the force on the undamaged structure below was less when it was falling than before it fell, especially since the towers were designed with large safety factors and much of the structure was blown outside the footprint and away from the lower undamaged structure. The wedge uniformly accelerated because the force from my hand squeezing the log together was removed first, allowing it to uniformly accelerate down. The bowling ball uniformly accelerated because the force from the fishing line holding the ball was removed first, allowing it to uniformly accelerate down. The block on the jack uniformly accelerated because the supports were pulled first, allowing it to uniformly accelerate down. And the towers uniformly accelerated because the underlying supports were blown out first, allowing it to uniformly accelerate. The floors did not pancake because the impacts will not allow the upper roof to uniformly accelerate, but explosives, blowing out the lower structure, will allow the uniform acceleration we observed. The uniform acceleration of the upper falling body is a consequence of, but not the cause of, the destruction of the upward force that once supported it. But if you think I'm wrong and believe NIST, the media, the authorities, and our politicians, then prove me wrong by experiment. Because either all those authorities are wrong, or Newton's fundamental laws of motion are wrong. It's your choice, and you can believe what you want, but both Newton and NIST cannot be right. But it wouldn't be the first time in history that all the authorities are wrong. Just ask Galileo. Newton knows exactly what happened that day.